Hi, in this video we're going to be talking about trigonometric substitutions. And what trigonometric substitutions is, the concept behind it is we take an algebraic integral that we can't normally solve through standard means of integration, and we transform it using some substitutions of the right triangle, and we transform it into an integral with trig functions in it. And then by integrating this trig function, we can actually solve the integral and either get a number if it's a definite integral, or we can get a value in x or whatever variable we started with just by doing reverse substitutions. Now, there are three types of integrals. There are the types with a squared plus x squared in them. There are the types with a squared minus x squared in them. And there are the types with x squared minus a squared in them. So you might have noticed there's sine and cosine, which is what's going to appear in part 2 if we have that form. And if we have a form like this, we're going to let x equal the sine of theta. Now if we have a squared plus x squared, we're going to let x, I guess it's going to be a sine theta. We're going to let x equal a tangent theta. And if we have x squared minus a squared, we're going to let x equal a secant theta. And we'll see through examples why we do this, and that looking at an example. So we have 1 plus 4x squared. So this is of the form a squared plus u squared. Right? And what we can do is we can let u equal the tangent of theta. So what is u in this case? So we're going to let 4x, not quite 4x, but 4x squared is our u squared. So u in this case is going to be 2x. And we're going to let 2x equal the tangent of theta. So what does that tell us about the derivative? That tells us that 2 dx is equal to 2 secant squared theta d theta. And it also tells us that 1 plus 4x squared is going to be equal to 1 plus tangent squared of theta. And as we know, that is equal to secant squared of theta. So we can make our substitution in here where we have the square root of secant squared theta, and u is equal to, or 2 dx is equal to 2 secant squared theta, which tells us that dx is just equal to secant squared theta. So secant squared theta d theta. And by simplifying inside the integrand, we get secant cubed theta d theta, which, if you remember, is quite a mess. So I just took the result from the last video and pasted it in here, replacing x with theta. Now, we have that 4x is equal to tan theta. And I always make that mistake, but it's actually 2x is equal to tangent of theta. So how do we figure out what secant of theta is? So what we're going to do is draw a triangle. And we're just going to label this side theta, and we're going to make sure it's a right triangle. So we know that the tangent is the opposite side over the adjacent side. And by the Pythagorean theorem, we know that the hypotenuse is 1 plus 4x squared. So if 2x is tangent of theta, then secant of theta is the hypotenuse over the adjacent side. So that is going to be the square root of 1 plus 4x squared, which we've already seen right up here with our substitution from here to here. Okay, so let's just write it down here. 2x is equal to tan theta, and the square root of 1 plus 4x squared is equal to secant theta. Now we don't need any other trig forms here, so let's just go ahead and plug everything in. So we have 2x square root of 1 plus 4x squared plus the log of 2x plus the square root of 1 plus 4x squared all over 2. Okay. Now for our next one, let's look at the area of a circle. So area of a circle. And let's just go ahead and draw a circle here, or as close as we can get, and put some axes on it. Oops. I'll just go ahead and put some axes on it, like maybe here, and then we'll slide them up. And that looks like about a circle centered at the origin. So let's verify that the area with radius A is equal to pi A squared. So we know that the upper half is given by the equation f of x equals the square root of x squared, or a squared minus x squared. So a squared minus x squared. Now on the interval from 0 to a, we have a quarter of the circle. Okay, so if we look at these, this interval from 0 to a, so 0, and we have a here, we have this region highlighted in gold. So all we need to do is take the integral of f of x from 0 to a. That gives us 1/4 of the circle, and we multiply it by 4. So we have 4 integral from 0 to a of the square root of a squared minus x squared dx. And what we're now going to do is we're going to use trigonometry to figure out what's going on. So we're going to let u equal a sine of theta, or x in our case, because it's a squared minus u squared. So u is x, which is going to be a sine of theta. Then that tells us that dx is going to be a cosine of theta. And let's go ahead and draw our triangle now to figure out what a squared minus x squared is. So if this is theta, we have x over a is equal to the sine of theta. So sine is opposite over hypotenuse, and then using the Pythagorean theorem, we get that this is a squared minus x squared. And so the square root of a squared minus x squared is going to be a cosine of theta, because cosine is adjacent over hypotenuse, so cosine is the square root over a, and we'll move the a over. So replacing it in here, we get a cosine theta times a cosine theta, where a squared minus x squared goes to the first one, and dx goes to this guy, d theta. Okay, so now let's just go ahead and paste it down so we can actually work with it. So now we have this integral that we want to evaluate. And I think right there is pretty good. So we have 4 times the integral of a squared cosine squared theta, d theta. And we can pull that a squared out. So a squared, the integral of cosine squared theta, d theta. Now how do we deal with cosine squared? Now if we remember, cosine squared of theta is equal to 1 plus the cosine of 2 theta over 2. So let's just go ahead and place that in there. So we get 4a squared, integral of 1/2 plus cosine 2 theta over 2 d theta. Notice that when I converted to theta, I didn't quite change my bounds. So we're going to have to go back and do that at a later time if it's easier to integrate in the theta world. If it's easier to evaluate the integral in the x world, we're just going to go back to the x's and then evaluate our integral. So we're going to hold off on it for now, even though we could have done it in the beginning. Now we can split up this integral, and we'll get 2a squared integral of theta, or integral of d theta, plus 2a squared integral of cosine 2 theta d theta. Now the integral of d theta is just theta, so 2a squared theta plus 2a squared, the cosine of 2 theta, we're going to let u equal 2 theta, and so du is 2 d theta. We multiply by a 2 and divide by a 2, and we can get rid of this 2 here. And so we have the integral of cosine u du, and remember that's just sine of u, which is sine of 2 theta. Now, what else can we do here? Well, we can factor out that a squared, so we get a squared times 2 theta plus sine 2 theta. And now let's go and see what theta is, because we have to substitute it back if we're going back into the x world. And if sine of theta is x over a, theta is arc sine of x over a, and that's kind of a little messy. So let's go ahead and figure out what 0 and a are in the theta world. So 0 in the x world goes to something in the theta world, and a in the x world goes to something in the theta world. So remember that sine of theta is equal to x over a. Okay, so 0 in the x world is going to be, well, that tells us that x is equal to a sine theta, or theta is equal to arc sine of x over a. So arc sine of 0 over A is the arc sine of 0 is 0. And here, A is the arc goes to the arc sine of 1. So the arc sine of 1, we're solving sine of theta equals 1. And if you remember your graph of the sine, 1 is right here, and that's at pi over 2. So pi over 2 in the theta world. So we're evaluating this integral from 0 to pi over 2. And when we make this substitution, we have a squared times pi plus the sine of pi, which is 0. And then we're going to subtract what happens when we plug in 0. So we have 0 plus the sine of 0, and this just all goes away. And we have pi a squared, which is the area of a circle.